Okay, so one of the things that I wanted to do for you guys was to give you, I don't know, as good a walkthrough of these notes as I possibly could. So, the last 2 weeks we've done nothing but talk about waves, how they can differentiate one from another in terms of your transverse wave and your longitudinal waves. We've talked about period and frequency and all the different ways that you could measure it. So now we're going to start getting into actual real life applications of them, not just these are the generics of a wave. Now we're going to be applying it to real things. So our first example for the remainder of the year is going to be sound. Then we're going to move into light. So if you want to follow along with your textbook, you can absolutely. It's chapter 15, but this is sound in general. So one of the things to keep in mind is that with these waves that we're talking about, we see them all the time. This could be in a wave pool at whatever amusement park you'd go to whenever they reopen again, all the way up to something as extreme as a tsunami. I'm going to use the tsunamis as my example, not because there's anything here that you need to write down. Remember that the only stuff you really need to write down is going to be something you see in red, but as a explanation as to one of the things I think most of us missed in our last part of this unit from last week, and that was what happens with a wave, how things move, whether or not it is individual particles moving from point A to point B and things like that. So a tsunami is made from an earthquake that occurs off the coast. There was a really, really big one in India in 2004. Literally what happens with these massive waves, tidal waves, tsunamis, is the earth moves, pushes some water out of the way, and as you can see right here, when it moves, all of that gets buckled up, and you begin having some of those waves that then travel towards the surface, towards the shore where people are going to be. So in India in 2004, there was a really, really, really large earthquake off the coast of Indonesia right here. It was, I don't remember what the magnitude, 9, there it was, magnitude of 9.2. And what happened was when that earthquake occurred, there was a ripple that was sent out, just like in any other pool or body of water, in all of these different directions. Indonesia obviously had to deal with the earthquake, but everyone else, specifically this coast of India right here, had to deal with the massive wave or wall of water that was headed their way. It moved the Earth's crust up about 2 inches. It was very, very, very large earthquake. But the idea, the point behind it, was that that wall of water was massive by the time it reached Indonesia. Right here, it was over 30 meters tall, over 100 feet. Estimated damage was somewhere in the billions. Hundreds of thousands of people died. Things got wiped out. It was pretty bad. But my point, waves, was it the individual water molecules that moved, or as the Earth moved up those 2 inches, was it the individual water molecule that first got pushed under the ocean that moved all the way across the Gulf right there and then slammed into India? No, no, it wasn't. It was that's hundreds of miles. An individual particle is not going to do that, but it was energy from those from that earthquake that caused all of that water to be moving. So it's the energy that travels from point A to point B, kind of like in a ballpark for a baseball game when the crowd does the wave. One person doesn't make one big long trip all the way around. It is the wave itself that makes the trip, not the individuals from their seat. You stay seated in whatever seat that you were. You don't get to move all that much. So it wasn't an individual water molecule from this location that traveled all the way, but what happened was it was like a series of dominoes. One water molecule bumped into the one next to it, and then it bumped into the molecule next to it, and so on and so forth, and you had this massive wall of water that wound up slamming into the coast of India because of it. Now, waves and sound in general, sound travels the exact same way that that wall of water traveled. That was my point behind it. Sound, as it leaves your voice or whatever object it was that was producing that sound, travels the exact same way those water molecules in the ocean did. They carry energy. They collide with the particles next to them. This is why some sounds you can hear, some are barely or cannot hear, some are barely noticeable, and some are downright painful. It all has to do with how much energy was put into those waves. As they travel from location to location. So a sound wave, the definition of it, obviously this was one of the things that you were going to need All waves carry energy. It's not individual particles that are moving from point A to point B. It's the energy. They collide with something next to them. And then that collision just happens again and again and again, like a chain of dominoes. So sound waves are pressure variations transmitted through a medium. I've used that word a lot lately. Medium is literally just the stuff the wave is traveling through. So if you're talking about sound in the air right now, for you to be able to hear this little spiel that I'm doing from YouTube, the medium is going to be the air in the room. If it were dolphins talking to one another under the water, then the medium is water. If it was the earthquake that we were talking about in India back in '04, then if you were to feel the earthquake and your feet shaking from it as the earth moves beneath you, the medium would be the dirt. And that's all this is. So we've got, let me get my, there you go, I erased everything. And so the analogy between transverse and longitudinal waves that we were using is that they're both waves. They both transmit energy. With a transverse wave, you have that amplitude that is perpendicular to the direction the wave is moving. If the wave was moving, in this case, left to right, then your amplitude is going to be up and down, perpendicular to it, whereas you have the exact opposite in a longitudinal wave. In a longitudinal wave, these particles of air are moving forward and backwards. And so they'll move forward and bump into the particles next to them and then wind up coming back, kind of like a pendulum swinging back and forth. You just can't see them because they're so small, but that's what winds up happening with them. And so those are longitudinal versus transverse waves. Sound travels as a longitudinal wave. We'll talk about it a lot here in a little bit. Obviously, we've got our two different parts: compression right here, where all those particles get squeezed together, versus rarefaction, which is kind of like the breath in between those compressions. It's the pause. It's a region where there's a lot of empty space in between those particles. The material that wave moves through is incredibly important. Because sound doesn't travel the same. You guys probably noticed this before. If you're outside on a cold winter day shoveling snow, sound just appears to travel differently than it would on a really hot summer day where someone's down the road playing basketball, or even underwater. If you were to submerge your head underwater and listen to someone try and talk to you, it's not going to be the same sort of sound you would hear in the air. So the stuff the sound is traveling through influences how that sound travels in general. And so that's where this comes in. It's really got to do with the density of the medium, the density of the material that that object is, that wave is trying to move through. So the more dense the material is going to be, the faster that sound is going to be. It's like a more crowded concert. If everyone's falling on top of one another, yeah, we'll continue with this one. If everyone's falling on top of one another, the more crowded it is, the more likely you are to fall on the person next to you. Whereas if you're spaced out a little bit, you might fall and then not transmit that energy to the person next to you at all because there was space between you guys. You can think about it like dominoes too. If you've got all of your dominoes really close together and you knock one over, all of them are going to fall. But the more space you get in between them, you might get a point where one domino falls and it just doesn't knock over the domino next to it because there's not a particle right next to it. There's not a domino right next to it. So more dense medium means you're going to have a much faster speed of sound. A less dense medium means you're going to have a much slower speed of sound. And it's all got to come back to those particle pictures that I'm sure you guys looked at last year in chemistry. In a gas, any change, any variation, any bump to this one tiny little particle over here may or may not get felt by this particle. It may or may not get felt by this particle or this particle, but it likely will not be noticed by this particle all the way up here anytime soon. They've all got to keep moving and colliding with one another in order for that energy to be transmitted. Liquids, they're a little bit closer together, but you'll notice there's still some gaps around these particles, and so any motion in this individual particle, while it would be felt by the three particles closest to it, there's some space there. It's going to take a little bit of time, whereas if you've got a solid, there is no space in between any of these particles. So if this particle down here begins moving, it's immediately felt by these three, and then immediately felt by these five, and then immediately felt by these seven, right? And it's just going to keep going and going. Propagating is what we refer to it as it spreads outward in all directions. And so the more dense the medium is, the faster sound travels. It's because there's less space between those atoms. There's more collisions that are going to occur as one of those particles begins moving. So here's a little data table. You have to memorize none of these numbers, so don't worry. But we've got the different medium that the sound wave could be traveling through, and all these things are things that we've measured. If we were in class, I would do a lab where you guys would be able to measure the temperature in the room based on how quickly sound traveled, but we're not going to get into that. What I do want you to notice is speed. So in air, it's around 330, 340 meters per second. But once you get down here to water, it begins getting faster. It gets tremendously faster, about 4 times as fast, 4 to 5 times as fast, moving from air into water. Salt water is even faster than regular water was, because again, you've got all that dissolved salt inside the water. So now you've got more stuff, more particles inside that solution, more likely to transmit that energy from place to place. Rubber has about the same density as salt water, which is kind of why it floats sometimes, most of the time. But in this case, sound's going to be able to travel at about the same speed. And then iron, a solid metal iron, where all of those particles are really close together, you're going to have the fastest speed of sound. This is why sometimes in those old Western movies you'd see Native American chiefs or train robbers put their ears to the railroad tracks or to the ground listening for a herd of buffalo. You could hear the sound coming through the earth a lot sooner than you ever would coming through the air, because it travels 10, 12 times faster through those solid objects, right? You always notice the earthquake before you get the tsunami, and that's actually how we get that tsunami detection stuff that we use. The earthquake hits, and based on the magnitude, they're able to determine how likely it is that a really big wave is on its way. The speed of sound in air is something that we can calculate, and this is one of the only new equations that you guys are going to have. The warmer the medium is, as you might have noticed on that last data table, the faster sound travels as well, again, because those particles are colliding more often. The hotter it is, the more often they collide. So the more likely you are to send that sound wave from location to location. So the equation that I want you guys using for assignment 1 and for this unit in general is velocity is equal to 331. That's actually the speed at which sound would travel at 0 degrees Celsius, plus 0.59 multiplied by your temperature in Celsius. So this is the equation that we're going to be using whenever we're trying to figure out how fast sound is moving, or in the lab we would have done if we'd been in class. You would have found out how fast sound was moving from location to location and then worked backwards to find your temperature. That's all that would have been. A couple quick practice problems, and for number 1, I want you guys, now that it's up, hit pause, give it a try. You've got your temperature that was provided here, and so with that temperature, you should be able to work through the equation that we just went over. So hit pause, give it a shot. What we were provided was 28 degrees Celsius. You've got your velocity that you're looking for. Everything else in the equation is a constant. It's something that you already know. So you plug in your 28 degrees Celsius, multiply 0.59 and 28, add it to 331. Yes, you can have negative temperatures. It just means the speed of sound would be less than 331. It's not something we have to worry about in this case. You should get 347.52. I'm not worried about how many decimal points you keep or anything like that for this particular unit. The next problem, at the speed of sound in our physics classroom, was 344.2 meters per second. What would the temperature in that room be? Again, it should be the same equation. Hit pause, give it a shot, see what you can do. Again, it's the same setup. The one thing I want to make note of here, because there'll be a problem like this on the mini exam, mini test that you've got to do, order of operations. Remember to move the 331 first. Don't do 331 plus 0.59 and then subtract it or divide it from both sides. Make sure you move 331 first. When you move 331, you should get about 13 and a half. Then you can divide it by 0.59, 0.6. However you want to round it, doesn't matter, but you should get around 23 degrees Celsius. Now, the parts of sound. This is going to be a little bit different in terms of concepts. This is basically just taking the vocabulary that you already have and applying it to where we need to be, or applying it to sound the way we need to. So pitch. Oftentimes when musicians or vocalists or whomever talk about the pitch of a sound wave, they're referring to the frequency that sound wave has. I know I was just working through making some practice problems for you guys for this particular unit, and I found out middle C is exactly 262 hertz. It is the frequency of that sound wave, and for anyone musically inclined, I most definitely am not. That would be a middle C on a piano or a violin. This is oftentimes going to be referred to as a note being played on a musical scale. If you're familiar with those, obviously you know each one of those different notes that you can have is a very distinct separate frequency. Loudness is a little bit different. Loudness, how loud something appears, because you can have a really high-pitched sound but a really low volume. Loudness or volume is determined by amplitude. What I wanted you to remember from before, our last unit, was that amplitude is determined by the amount of energy that that source has. So you don't have to put a lot of energy into a high-pitched, quiet note, but you would have to put a lot of energy into a high-pitched, loud note, very high volume. It's proportional to that amount of energy. This is oftentimes why you can actually, if you turn the volume all the way up on your speakers, why you can see the surface of your speaker drum actually moving. It's literally moving up and down, pushing air, compressing air that is right next to the surface of the speaker. And the more energy you want to put into it, the louder you want it to be, the more it has to compress that air, the higher the amplitude. The louder the sound. That's really it. We measure this using a scale we refer to as decibels. Bell is the base unit that we were going to use. The prefix deci is a factor of 10 smaller than a regular bell, but we use decibels to describe most sounds. It's a logarithmic sort of scale. So while we're not going to don't panic with this, we're not going to do any logarithms in this class. Even during a regular school year, I wouldn't teach you logarithms just to do this. There's an easier way to get around how to figure out exactly how loud something is on a decibel scale. Typical number scales where 1 is twice as much as 2 or 2 is twice as much as 4 don't apply here in any way, shape, or form. Every increase of 10 decibels on a logarithmic scale means that it's going to be a sound that is 10 times louder. That sound that is 10 times louder then gets amplified. If it's 20 decibels, now it's 100 times louder. And then the next 10, it's 1,000 times louder. So 0 decibels would be one of the lowest limits of human hearing on average. Volume of 10 decibels is 10 times louder than 0 decibels. 0 doesn't mean it's non-existent. It's just the minimum threshold for humans. We're egocentric enough like that to where we decided to make 0 where we can stop hearing, not, dog, cats, or other animals. So 10 decibels is 10 times louder than 0. 20 decibels is going to be 100 times louder than 0. 30 is 1,000. 40 is 1,000 times louder than 10 decibels. Notice that's not 0. It'd be 10,000 times louder than 0 decibels, but it's 1,000 times louder than 10 decibels. There is a shortcut for figuring this out. There's nothing that you have to memorize, and I want to show you guys that shortcut here real quick. If you were to take this number right here, right, you're going from 30 to 0. So from 30 to 0, you're going to have a factor of 3, logarithmic factor of 3 times louder, basically. So what that means is that with that 3, you're going to add 3 zeros, and that would give you 1,000 times louder. If it's a difference of 20 decibels, then you're going to have 2 zeros. Again, down here, 40 decibels to 10 decibels, you get a difference of 30 decibels, 40 minus 10. And so again, with that 30 decibel difference, you're going to get 1, 2, and 3 zeros. So it's always a little bit easier to figure it out that way, I think, than trying to fool around with logarithms. To give you a little bit of a sense of scale, this is what a lot of the most common things you would hear would rate on the decibel system. I can't, and most people can't hear the ticking of a basic watch, but that would be down here at 20 decibels. Quiet library would be around 40, normal conversations 55 to 65. The lawnmower that you guys probably ran the other day because it was nice is around 90 decibels. And then all the way up here is literally every Rise Against or Foo Fighters concert that I've ever been to, right? Probably have some sort of hearing loss, but that's okay. It was worth it. So just want to give you guys a sense of scale for that whole decibel system. We'll do a couple practice problems with it. Back to constructive and destructive interference. This is important because it gets to the heart of music and why music works the way that it does. When those two waves with similar frequencies overlap in a medium, and it doesn't have to be just similar frequencies, but if the frequencies are too different, we would never notice that this can happen. they're going to constructively interfere and destructively interfere simultaneously because they're not the same frequency. If they were the same frequency, you could generate a standing wave, just like you guys went over in the mini exam last week's unit. But if they're not the same, what you'll notice in the gizmo that you should be working on tomorrow is that you'll wind up with areas where they constructively interfere, followed by areas where they destructively interfere, and they'll alternate. That alternating pattern that you're going to notice in the gizmo is what we call beats. And this could be the beats of a, hip hop song. It could be any music in general. One of the things I was just thinking of was orchestras when they warm up. At the beginning of an orchestra show, my younger sister played the violin for almost a decade. She was really good. But every time they were to start one of her concerts, I always thought when they all just sit there and play the same note for about 4 minutes, they were telling everyone to sit down and be quiet. They weren't. They were actually tuning all of their violins or cellos or whatever, making sure they all have the same frequency and they're all in tune with one another. What they were doing was looking for beats between their instrument and the sound around them. My ears were never good enough to pick this up, but if you're out of tune, you'll hear a small beat reoccurring again and again and again. And it literally just comes down to being the difference between the frequencies. Musicians tune their instruments to the point where they actually hear absolutely no beats in between them. And that's the goal. That's when you know that you got your instrument in tune, is when you're not able to hear, they're basically a beat frequency of 0. You're not able to hear any of that at all. So those practice problems again, this should lead right in with assignment 1. In fact, these are the first 4 on assignment 1. How many times louder would a 120 decibel jet engine be than a lawnmower? So hit pause, take a moment, try and figure it out. Remember that it's the difference between the two of them. You've got a 40 decibel difference between them, and so that 4 told you exactly how many zeros there should be, and it's going to be 10,000 times louder. That's my little shortcut for the whole thing. For number 2, 320 hertz tuning fork played at the same time as the 328 hertz tuning fork. Give it a shot, try and figure out what that beat frequency is, hit pause. Again, it literally just comes down to the difference between them. You might have seen in the equation on the previous page, there were absolute value brackets there. Just ignore the negative when you get a negative. It's not the end of the world. But that was it. Some other vocab terms that are going to pop up throughout the course of this little unit that we're doing on sound, just some things that people use in everyday language, vocabulary, conversations that you probably never thought of. Echoes. Echoes are literally just those sound waves, those traveling pressure waves hitting a rigid boundary and returning. The field house is probably empty at the school, so if you ever get to go back there, you could try it. Shout real loud in the corner, and the sound wave will travel to the other end of the building, bounce off the walls, and come back to you. It's far enough, and sound travels slow enough to where you actually get a pretty decent echo out of the whole thing. But this is also how bats, dolphins, and all those other animals get around using echolocation. They send out some really high frequency sound waves. They collide with objects and then return. And based on how long it takes for that sound wave to return, they know how far away another object is. We'll talk about Doppler shifts and how we use sonar and all that next week. But that's the basics. That's what it is. This is also what they do with acoustics inside concert halls. And the reason that concert halls are built so specifically and so expensively is you want to try and get those sound waves reflected back off of the walls and back to the audience in phase, not out of phase. If they're out of phase, you'll have destructive interference. You want to have constructive interference occurring right here at the seats for all the people so that you get that really nice loud sound coming from a stage that is really, really far away. You normally wouldn't hear a loud sound with. That's how they go about trying to build and design those really fancy stages like Carnegie Hall and a couple of others. That was their goal. That's why those audio engineers get paid so much. Natural frequency. This is a good one because it's going to deal with resonance, and resonance is one of the cooler things that we can talk about with sound. It was meant to be its whole new unit, or half of the unit after this. We're not going to get to it, but I want you to know what resonance is. so that you don't think this is witchcraft or something like that if you were to ever see it in real life. The natural frequency, every object has a natural frequency with which it'll resonate at, with which it will oscillate, vibrate, move back and forth, where very, 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 very little energy is needed to keep it moving. It's like a kid on the swing set. When you get your legs timed up correctly, it doesn't take a lot of effort to keep going once you're moving there. It's the same idea. Every chemical bond, every object in the universe has, if it's a cohesive, what is the word I'm looking for? Homozygous sort of thing, right? There's only one type of material inside of it. It's solid all the way through, consistent, 100% zinc or 100% lead or whatever. Humans, we've got a bunch of different things inside of us. We've got blood, muscles, tissues, bone. All of them have their own unique natural frequencies. But it's the frequency at which these things will vibrate at very, very, very easily. Resonance itself occurs when really, really, really small recurring forces are applied to an object at regular intervals, basically a kid on a swing set kicking their feet at the right time, cause a dramatic increase in amplitude. That dramatic increase in amplitude looks really cool because you can actually see the object itself moving. You can see the wave pattern inside of it. But the downside to that is that increase in amplitude of too much can actually break those chemical bonds. And so I've got a couple of videos here that I'm also going to link. I encourage you guys to check them out. The first one's pretty basic and silly. It is just a kid on a swing set. But the next one, the Tacoma Narrows Bridge, I really encourage you guys to check that one out. This was a bridge that was built in, I believe, Nevada, Arizona, somewhere out that way. And they didn't take into account, it was a suspension bridge like the Golden Gate Bridge or any of those other ones with the really long cables holding it all up. What they didn't take into account was the wind going through the cables. And it's kind of like people can do with a piece of grass between their thumbs, or they blow through it and they get a really high pitched sound. The wind going through that was actually causing the entire bridge to resonate. And there's a massive standing wave that was generated on the bridge. It looks awesome. Unfortunately, they did have a very large increase in amplitude because it had hit its resonant frequency, and the whole thing came crashing down. Too much amplitude, too much sway, literally snapped the concrete that was holding the bridge together. And then I caution you with the volume on this third video. I really like this. It's a clip from the Mythbusters, or a guy who was on the Mythbusters. I think it's a newscast. Anyways, it's one of those opera singer sort of individuals using their voice to shatter wine glasses, getting the right pitch and the right frequency, same thing, sorry, but getting the right frequency of note to be played where the entire crystal wine glass hits its resonant frequency, the whole thing starts shaking and they catch it on the high speed. It looks really, really, really cool. And so you kind of see the destructive side of resonance. It's a pretty neat video, but keep your volume down for that.